everybody for sticking it out. It's me, louder. He's going to be talking. I'm just going to give a very quick introduction. I'm not saying anything important. Although this is actually the session I'm most excited about for the entire week. No offense to the other speakers, whose talks are great. But what I like here is that we have this interesting resurgence of interest in interior point methods. It's our pleasure to have Steve Wright give kind of the first two lectures, kind of setting up perhaps what would be like a, what would you call this? The right view of how to think about interior point methods.
Oh no!
I don't know. With a W, right with a W. No, so we have kind of Steve was one of the pioneers in this area in the 90s and wrote my favorite text on the subject. And so he'll give the introduction, and then we'll get kind of the more contemporary view and the applications to kind of the discrete side of things from Aleksander Mądry and Aaron Sidford in the subsequent lectures. So without further ado, here's Steve Wright from the University of Wisconsin-Madison.
Great, thank you, Ben. It's such a pleasure to be here too. Okay, so here's an outline. I'm going to talk mostly about LP, and I think the two colleagues that are following me, Aaron and Aleksander, also are going to focus mostly on LP. Of course, interior points have a much broader scope than that, and I'll mention a few of those extensions here to quadratic and programming and LCP, linear complementarity. Okay, I'll talk a little bit, give you a bit of background about Newton's method, central path neighborhoods, primal dual path following. I'll spend a lot of the lecture on that. Talk a little bit at the end about primal and dual barrier methods, which are things that Aleksander and Aaron are more interested in, I would say. And then talk about the relationship between these barrier methods and these path following methods, the primal dual methods. So I'm not going to give too many citations, right? Because back in the 90s, there used to be flame wars would break out. You know, people would get very upset if you wouldn't credit the right people for the right ideas. Fortunately, that was the days before Twitter, so these flame wars would take place on email, so the bandwidth was a little bit more limited. But we certainly did our best to make our feelings felt in those days. But I do want to acknowledge that there were tremendous contributions, particularly towards the stuff I'm going to talk about, from people here in this program. So I'm going to run the risk of leaving important people out. But Yin-Yu Ye was a very important contributor. Jim Renegar back in the 90s. Levent contributed a lot. Okay, I'm already blanking. Am I missing out anyone? Certainly those three people, and I'm really sorry if I left your name off. Oh, Levin, of course. Sorry, Levin's name is up here. So if you want to look for more information about background, elaborations on what I've talked about, take a look in these books. There's The Classic Time of Nesterov and Nemirovsky in '94, published by Siam. There was my book from '97. Yin-Yu published a book around the same time. These are Levin's slides for his lectures for EE 236C, I think. Sorry if I got that wrong, at UCLA. But anyway, this is a very beautiful, concise summary of some of the main theories particularly surrounding barrier methods and self-concordancy, and sort of summarizes some of the important stuff on Nesterov and Nemirovsky in a very easy to understand form. And then Jim, I forgot to mention Jim. Okay, but Jim wrote this beautiful monograph in 2001 about the mathematical theory behind interior point methods. And he was one of the pioneers, actually going back to the 80s in this area. Okay, all right, so here's kind of a statement of philosophy that I just want to preface the talk by. There is beautiful theory underlying interior point methods, beautiful analysis, very elegant. It also required the development of kind of new areas of analysis, self-concordant functions, self-scale barrier functions and cones, primal dual potential functions, all of these ideas that came up in the 80s and 90s. And this theory is really important in going beyond LP to more general conic programming, particularly to SDP. You need this very elegant general formulation to make that jump. And here are some papers that sort of carry out that, that sort of work in that domain of that elegant general mathematical formulation. There's an SDP review paper by Todd. I've already mentioned this book. I've already mentioned Levin's slides, and I've already mentioned Jim's book. But all of these have, take that sort of mathematical viewpoint that's very refreshing and very powerful. However, the thesis of this talk is that you can get an amazing amount done using very elementary mathematical tools. And that's the approach I'm going to take today, most of the time. Towards the end, I'll switch and make the connections, a few of the connections with this theory. But I do want to stress and I do want to demonstrate to you that you need to know almost no math to prove polynomial complexity of an algorithm to solve LP. And I think that's really remarkable, that you can do so much with such limited tools. And in fact, I'm going to give you a complete polynomial convergence proof and demonstrate to you that it is possible to do it using very basic tools, even after lunch, okay, which is always a challenge. Okay, so some reviews of linear programming. So just to maybe fix notation and to remind you of some of the basic theory. So this is a notation I'll use, minimize a linear function over a polyhedron. Polyhedron defined, this is what some people call standard form. I guess it's what I call standard form, where the general constraints are equalities and the x's are constrained to be non-negative variables. A is an n by n real matrix, and I'm going to assume full rank, although that issue doesn't come up much, except when it comes to solving linear systems, which you have to do, and then you sort of need full rankness to get well-posedness of the linear system and so on. So let's assume we've got full rank. You can always do pre-processing if necessary to make sure that's true. Okay, so you can write down a dual of this, maximize B transpose Z, where B is from the right-hand side here. A transpose Z less than or equal to C. A again is the matrix. C is the primal objective. And you can introduce dual slack. So you can introduce S to capture the difference between the left and right-hand side here and the dual constraints. So that's the way that we'll stick to. This is a formulation we'll use, where the dual variables are Z and S is non-negative. Okay. And then you can write down KKT conditions, Karush-Kuntaka conditions, which are optimality conditions simultaneously for the primal and dual. So these involve both primal and dual variables. They consist of the feasibility conditions for the primal and dual problem, with one extra condition added, this crucial condition of complementarity that says that the x and s vectors have to be complementary to each other. So that means that their inner product has to be 0. That's one way of saying it. Another implication of the non-negativity combined with the complementarity is that all of the components of x and all of the components of s have to be non-negative, obviously. And if you take pairwise products of xi times si, that has to be 0. In other words, one of the two needs to be 0, at least, for all I. Okay? So that's a condition that's kind of hard to satisfy, because it's the only non-linear condition here. All the other conditions are linear. All right. So there's a theorem that says if you've got a triple xzs satisfying these conditions, then the x solves the primal problem and the zs solves the dual. Okay? All right. LP duality, very powerful theory developed, I guess, in the 50s mostly. First of all, there's weak duality, and that just says if you've got a feasible point for the primal and a feasible point for the dual, then the primal objective, the thing you're trying to minimize, is bigger than or equal to the dual objective, which is the thing you're trying to maximize. And on Monday, that was proved twice on Monday, I think by Pablo, maybe Pablo and someone else. So I won't do it again. Well, actually I will. It's on the next slide. Okay? It's hard to avoid writing down that proof, because it literally is a one-line proof. Okay, literally a one-line proof. Okay, strong duality. This is a very powerful theorem. This says that if you consider the primal and dual pair, exactly one of these three things is true. Okay? The first thing that's possibly true is that they both have solutions, the primal and the dual, and at optimality, their objectives are equal. Okay? That's the first possibility. The second possibility is one of the two is unbounded and the other was infeasible. Unbounded means it's feasible, but you can drive the objective to infinity or minus infinity on the feasible region. Okay? So that's the second possibility. And the third one is that they're both infeasible. So this doesn't cover all the bases. You know, this theorem tells you that, for example, you can't have one problem being infeasible and the other one having a solution. You can't have one problem being unbounded and the other one having a solution. Moreover, it tells you if they both have solutions, the objectives are equal. So this actually says a lot, this theorem. And this proof is actually, the other thing to notice is it doesn't need a Slater condition. When you prove this for STP, very often you need a strictly interior point. That's not true in linear programming. Okay? You can get away with a lot more in LP. The proof is a lot trickier than weak duality. In fact, one of the standard proofs uses the fact that there is a method that solves these problems, namely the simplex method, and that if you apply the simplex method with appropriate rules for avoiding cycling and so on, it's guaranteed to terminate. Okay? So you actually need the algorithm to prove the theorem, which is slightly weird state of affairs. But there are other proofs as well, but they're certainly more complicated than the one-line proof here. Okay, so what about duality and complementarity? Well, if you've got a pair, for most of the talk I'm going to be assuming that your primal and dual candidate iterates satisfy all the easy conditions. They satisfy the equality constraints and these inequalities. They're all linear. And so when you're considering methods that generate iterates, and I'm going to be talking primal dual methods, so it generates iterates in the primal and dual space simultaneously, they're going to satisfy all of these conditions. And if you've got a point that's primal dual feasible, then here is the one-line proof again. Okay, if you take the inner product of x and s, because both of these vectors contain non-negative entries, their inner product is greater than or equal to 0. If I substitute for s from this condition here, I get an equality. If I just expand that out, I get here a times x transpose z. A times x equals b. Okay, so that second condition collapses to b transpose z. And there we have that c transpose x is greater than or equal to b transpose z again. Okay? So the reason I wrote this out, though, was not to give you a third proof of weak duality, but rather to point out that one way to keep track of how close we are to optimality is to keep track of this inner product. And in fact, we denote this by mu. We denote mu to be 1 over n times that inner product. And that's the thing that we're going to try to drive to 0. Because if we're maintaining all these conditions and we drive this to 0, we're heading for a solution, okay? Primal dual solution. So this mu is a very important quantity. Another way to think about it is it's the average value of the xi times si pairs, okay? It's the average of all of these pairs, all of which need to go to 0 at the solution.
Sorry, quick.
Yeah.
I mean, you could have measured also the difference between the dual and the primal objective function.
Yeah, it turns out it's the same, right?
Is the same as mu? No, mu is
it's n times mu. Okay, so if these points are all feasible, if these conditions are satisfied, that's exactly the same thing. Yeah. Okay, so we're going to use this notation a lot where we take a vector and make it into a diagonal matrix. So I take the components of x, string them out along a diagonal, put zeros everywhere else in the off diagonals, and I get a matrix big X. Same thing for S. And then also I'll use a lot this vector E, which is just a vector of all ones. Okay? So using that notation, I can rewrite the KKT conditions like this, where here's the primal feasibility, here's dual feasibility, here are the non-negativity constraints, and then the last condition here is a complementarity. So if I multiply x times s times e, I simply get this vector here, where the ith entry is just xi times si. Okay, and I want that to be 0 as well. So if I can find an x, z, and s that first of all satisfy these these nonlinear equations, that one's nonlinear, and these inequalities, I've got a primal dual solution. So what primal dual and interior point methods do is to try to solve that system. Okay, so that's the approach. And for most of the talk, I'll be talking about maintaining strict feasibility with respect to the easy conditions. Strict feasibility means I want the components of x and s to be strictly positive. That's why it's called an interior point method. Okay? Strict feasibility with respect to those conditions. And we need these equalities satisfied at all iterates. We're going to take Newton-like steps on this system. If you look at this system, it's a square system, right? The number of unknowns, if you count up the number of x's, z's, and s's, there's 2n plus m, where n is the number of rows in A, n is the number of columns. So there's 2n plus n unknowns. There's also 2n plus m equations here. So it's a nice square nonlinear system with these extra conditions added on. So we're going to, and I'll describe Newton's method in a moment, but we're going to take steps that kind of look like Newton's steps for that system. Well, let's denote them by this delta notation. We're going to take steps along that Newton direction, usually not full steps. Usually we're going to pick some alpha that's between 0 and 1. Because these conditions are linear, then after we take the step, they'll continue to be satisfied. I'll explain that more in the next few slides. We're going to make sure that we choose the alpha so that these conditions continue to be satisfied after we take the step. And we're hopefully also going to decrease the value of mu, okay? So as you move from xk to xk plus 1, hopefully mu will shrink as well. And we'll be able to say something about how fast it shrinks and thereby get convergence and complexity results. Okay? And here's the other critical thing that's really crucial to the success of these methods. We try to make the xi times si's all decrease to 0 at roughly the same rate. That's the secret. Okay? At roughly the same rate. So in other words, we sort of keep track of the ratio between xi, si, and mu, which is the average value of the xi, si's. And we want that ratio to more or less kind of stay bounded. Okay? Not go to 0. That can be done explicitly, as it will be in the methods that I'll talk about. It can also be done implicitly, which is what happens when you're using a primal dual barrier function. It basically maintains that condition, but in an implicit way. Okay, what about complexity? How do we get polynomiality? Well, what we're going to be able to show from these methods is you get a decrease in mu, this duality gap measure, from one iterate to the next. And typically the decrease is a factor of this form. 1 minus some constant, independent of n, times n to some power. Where this power here is typically 1/2, 1, or 2, depending on what method you're talking about. But usually in conventional interior point methods, at least 1/2. Okay? So you're guaranteed this factor of decrease in the mu at every step. That's typically what you can show. Now, everyone knows how to convert that into a complexity. Here's the standard argument. I want to figure out how many iterations will it take me before I can reduce mu k by a factor of epsilon over where I started, mu 0. Okay? Well, the number of iterations is going to be the value of k, such that this factor raised to the power k is less than epsilon. Okay? So I can take the log of both sides there. I can then use the fact that log of 1 plus t is less than or equal to t for all t greater than -1. Okay, we've got this very nice universal bound for the log. So I'll use that bound here to lower bound this log term. So then I get this condition. And now I simply divide both sides by minus c n to the minus mu. Because I'm dividing by a negative, the sign, the inequality flips around. And I get a lower bound on the number of iterations. Okay? So in other words, when you get this amount of decrease, that translates into a order n to the nu log epsilon iteration complexity count. All right? Yeah.
So you want to get a bound on the cost being tolerance epsilon. How do you translate a bound on mu into a bound on the
Well, that is the duality gap, right? So it measures the difference between primal and dual. So by definition, it's going to measure the difference between the primal and the primal optimal value, because the optimal value is sandwiched in between the two feasible values. Okay? Alrighty. So a little very slight diversion on Newton's method for nonlinear algebraic equations. This is something you probably all learned in your very first numerical analysis course. Back 30 years ago, I remember when I was a postdoc and my colleague Mike Shelley, who's now a very distinguished applied computational mathematician at Courant, and also he works for the Simons Institute in Manhattan. But he said to me at lunch one day, well, optimization is just Taylor's theorem. You know, that's it. That's the whole thing. And of course, that's not true, because as we've seen this week, there are many other, optimization brings in many other things. In the case of Newton's method, it kind of is true, you know, largely. So this is really just Taylor's theorem. This is the Taylor's theorem derivation of Newton's method. So the basic idea is if you've got a square nonlinear system of equations, mapping Rn to Rn, say, you can write down a first-order Taylor series approximation. This matrix J is the Jacobian. It's just the n by n matrix of first partial derivatives, where I take one of the components of f and differentiate with respect to one of the components of w. Okay? So this is the first-order Taylor series approximation. If f is smooth enough, then the remainder term is going to be little o of d. In fact, it's going to be o of d squared if things are sufficiently smooth. Okay, so the idea of Taylor's theorem, of Newton's method, is you just pick the d to make the first-order approximation 0. Okay, because after all, you want to find the value that makes f 0. So you pick the d to make that 0 at least, and then you define d to be that step. And that's given explicitly by just minus j to the minus 1 times f. Okay? So if I plug that into here, it zeroes out this part. All I'm left with is the order of d, or little o of d, which is little o of this. And so if the Jacobian is is non-singular at the solution, and you're close to the solution, W star say, then the inverse of the Jacobian is upper bounded, okay? And so this little o of d term turns into a little o of f of w term, okay? And so what does that mean? That means after you take the Newton step, you manage to reduce f of w to little o of f of w. So you get superlinear convergence. And if everything's smooth enough, it's going to actually be quadratic convergence, okay? So here is the picture you would have seen in like second year numerical analysis. Here is the equation, here's the f of w we're trying to find the zero of. We're trying to find that point there. And so in one dimension, j is just the slope, it's just the gradient. So if I start off at this point here, I take the slope at that point, I form a linear Taylor series approximation, and I find out where it crosses the x-axis, and I take that to be my next Taylor iterate, my next Newton iterate. So W0 moves to W1. I just repeat the process, and as you can see, I converge very quickly to the W star there. Okay? So that's an asymptotic result. That quadratic or superlinear convergence applies only when you're close to a solution. Sorry. I'll go back and cover those two slides in a second. But an interesting question that we should consider here when we're talking about interior point methods is what happens when you're outside that domain of quadratic fast convergence? That's really the issue here, because we're going to be applying Newton's method or this Newton idea far away from this domain of quadratic convergence. So you really need some sort of more global theory than what I've just shown you. In general, if you're just dealing with general functions, there isn't really any guarantee that Newton is any faster than a first order method. You can construct functions where Newton's method takes, as many iterates as a gradient method. However, these are very special functions we're dealing with here. They're almost linear except for that complementarity term. When you're dealing with barrier functions, and this is what I'm not going to talk about much, they have this property called self-concordance. And self-concordance is this beautiful property that says that the third derivatives, in some sense, are bounded in terms of the second derivative, so that the later terms in the Taylor series are not going to bite you too badly. By cutting it off at the first or second order approximation, you're not losing too much. So if you compute the Newton step and apply an appropriate scaling to it, you guarantee that you'll make a certain amount of progress. Okay? So that's really the key property here in showing that this Newton type approach has good global behavior. So going back to where I was, I'm sorry, I should have done this in sequence, but I told you about Newton's method for nonlinear equations because that's the important thing to talk about when we're doing primal dual methods. When you're doing barrier methods, primal or dual barrier methods, the more important topic is Newton's method for minimizing a function. So this is a function mapping Rn to R. Typically, I'll assume it's twice Lipschitz continuously differentiable. Here you take two orders of Taylor series approximation. You go out to the second order. And then you pick the D to be the one that minimizes this second order Taylor series approximation. And here is the formula. It looks a lot like the one that I had before. In fact, it's you get the same formula by applying Newton's method for nonlinear equations to just the gradient of f. You get exactly the same formula. Okay? In this minimization setting, though, there are a few more things that are sort of interest in analyzing interior point methods. The first one is if you plug the optimal D into this second order approximation, you can find out the predicted amount of decrease you're going to get over this step. So in moving from x to x plus d, it's telling you that f is going to decrease by about this amount or by about that amount. Okay, and so if you look at Levin's slides or the Nesterov-Nemirovsky book or many other papers on this topic, they introduce notation for this, lambda of x, and they call it the decrement. For this term here, and you can prove things about the decrement. You can prove things globally about the decrement. Notice I've got an approximate equals here, but in fact, if you've got this property of self-concordance going on, you can make this more rigorous. You can get rid of this approximate equals and put some sort of qualifier here and get some actual guarantee of at least a certain fraction of the predicted amount of decrease. And that's the key to polynomial complexity of primal or dual barrier methods. Okay, so getting back to path following, which is where I was a few slides ago. So this is a system that we're trying to solve. Actually, I've changed a little bit here. I've perturbed it by this factor here, tau times e. So remember, e is a vector of all ones. Tau is some positive parameter. So that's new here, this thing here. And this this thing is kind of the thing that stabilizes a little bit. Okay? So instead of heading right for the solution, we say, well, let's tweak the nonlinear equations a little bit to get a system that's a little bit easier to solve in some sense. Okay? So I'm going to think of the solution of this system as being as carving out something called the central path. And you can show that if the set of strictly feasible points for the primal and dual is non-empty, you can show that this system has a unique solution. For any positive tau, there's a unique triple, XZS, that satisfies this system. Okay, so the central path in primal dual space is well defined. And we're essentially going to use the central path as kind of the highway that we follow to the solution. That's the intuitive idea. So rather than taking Newton-like steps on that system I showed you a few slides ago, we're going to take Newton-like steps on this system. That's the idea. And it's a little bit less aggressive. Instead of making a beeline for the solution, we're actually heading for a point on the central path. Why do we do that? It means that we're less likely to bump into the boundary. Okay? The trouble with heading right for the real solution is you get stuck up against the boundary trying to satisfy these constraints. If you're a little bit less aggressive by choosing a positive value of tau, you're able to move a longer distance along the Newton direction before you bump into the boundary. Yeah?
So tau is the same for all the x.
Exactly. If I expand this out, it's telling me that xi times si is equal to tau for all I. Okay?
So it's not scale invariant. I mean, I could have scaled equations and things would change.
Yeah, I mean, everything is subject to scaling here. Yeah, that's true. You can mess it up if you take rows of A and start multiplying by huge numbers. You can make life more difficult. All right, so that's the idea. This is the very important concept in path following methods is the central path. That's the path that we follow. Okay, so we need to talk about neighborhoods because, of course, if we insist that we're always right on the central path, it's going to be a lot of work to get there. So usually we're satisfied with staying within certain neighborhoods. There are different ways to define neighborhoods, but what they all have in common is that you're trying to ensure that these products xi, si are not too different from each other. Okay? And one way to define them is to say, well, they're not too different from their average value, which is mu. Mu is the average value here. So there are a couple of ways to measure neighborhoods. These are the two most common ones. The first one says that if you take the vector of xi times si's, that vector where x1, s1, x2, s2, and so on down to xn, sn, and you subtract off the vector of mu's, which are their average values, that the 2 norm of that vector is less than or equal to theta times mu, where theta is something less than 1, between 0 and 1. So that's a 2 norm neighborhood. There's another one, which is the one I'm going to talk most about, which is a more generous neighborhood. That one just says you pick some value of gamma between 0 and 1. Typically, you choose it to be quite small, 10 to the minus 3, say. And you insist that all of the xi, si's are at least gamma times mu. So they're within a factor of 1,000 of their average value. Okay? There can't be, no one can be way closer to 0 than the others. Now, this is a more generous neighborhood than this one. If you let gamma go to 0, you eventually encompass the whole strictly feasible space. Okay? But if you let theta go to 1, that's not true. Even if theta is very close to 1, you're not approaching the whole strictly feasible space. And you can't let theta get bigger than 1, because then you'd start admitting terms where the xi times si is negative. So you can't allow that. Okay? So this neighborhood is more generous. This one actually gives nicer complexity results, though. As a factor of n, which I'll mention again a little bit later on.
Question.
Yeah.
I mean, just maybe jumping ahead a bit. I'm just curious. I've tried myself and I've gotten very confused. Is one of these like easy to relate to the Newton decrement? Like direct to relate to the Newton decrement?
Yeah, there's going to be some analysis about that. Yeah, and I've got some pictures as well. So hopefully they'll become clearer as we go. Okay, so here's a strategy. Oh, I changed the notation here, sorry. But the idea is we define a target point on the central path. We pick a value of tau, which kind of defines a point that we're heading for. We take a Newton step based on that system of algebraic equations towards that value. And then we choose a step length to move along that direction. We choose that step length so as to stay in whatever neighborhood we've chosen. Okay? And what we're going to be able to show, in fact, I'm going to work with that second neighborhood, the n infinity or n minus infinity neighborhood. What we're going to be able to show is you can stay in that neighborhood taking steps of this type and achieve this amount of decrement. So for some delta independent of n, you're able to show a decreased factor of 1 minus delta over n. And so that's going to translate into an n log epsilon complexity.
Sorry.
Yes?
Is the n infinity or is it a bit
That should be minus infinity.
right? What
That's this neighborhood here, when no pairwise product can be too much smaller than the average. Okay? All right, so here's the whole method. I'll call it long step path following. So this is a notation we use. I use this notation here to give you a step along the Newton direction at xk. All right, so it's just a shorthand for this. All right, so here's the strategy. You pick a gamma that defines the n minus infinity neighborhood. You pick sigma min and sigma max, they're both between 0 and 1. You choose an initial point, which has to be in the neighborhood. Okay, then at each iteration you do the following. You pick a sigma k, which is somewhere in that range, and the sigma k defines the target value of tau. So you define your target to be sigma k times mu k, where mu k is the current value of the average duality gap. So because the sigma k is less than 1, you're sort of aiming for a point that's a little bit further along the central path than where you are right now. Okay? The point on the central path that corresponds to this iterate, you can think of as being the mu k point. And we're trying to move from the mu k point to the sigma k mu k point. So we're aiming to make some progress. Okay, and sigma k is less than 1, so it's going to be closer to 0 than where we are now. Okay, so you calculate that Newton step. You then move along that direction as far as you can while staying within the n minus infinity neighborhood. And I'm going to show you in a moment that you can take a significant step. You don't immediately get jammed up against the boundary of the neighborhood. And then that's the step. Okay? That's all there is to it.
So
Yeah.
just to be pedantic, we are
Yeah.
ignoring initialization here.
Yes. Oh, yes. That's a very important point, which I talk about later on. Okay? So when I give you the complexity result, I'm taking this as a given. Okay? But yes, that's a very important point. We have to have a good way of generating a point in that neighborhood.
Steve, you're also going to say, is it simple to choose the largest alpha? Is that
Yes.
that's a simple.
To do that, you just have to solve a bunch of quadratics, because if you look at the way the n minus infinity is defined, it's xi times si greater than or equal to the average. Xi times si is just going to be quadratic in alpha, right? And the right-hand side, which is the mu corresponding to this, is also going to be quadratic in alpha. So you just have to solve you have to solve n quadratics in alpha, that's it. Okay, so that's order n. Yeah, take the smallest one, exactly, yeah. Okay, so let's dive into some of the details of this. First of all, this is the Newton step for f tau, where tau is sigma times mu. So I've just written down the Newton equations. That's the Jacobian of this system here. Okay, when I take the first partial derivative matrix of that system, it's almost all linear. So most of the terms in the Jacobian are actually constant. There's an A transpose, and there's identity here. Here it's not linear, but when I differentiate x times s times e with respect to x, I just get s left over. And when I differentiate with respect to s, I get x, okay? So that's where these terms come from. That's the derivative with respect to x. That's the derivative with respect to s. And then the right-hand side is just the current value of the function of that f of tau function at the current point. So I'm assuming that I'm currently feasible with respect to the linear equation. So those two values are 0. This is the residual with respect to the third block. So I plug in the current x and s here. I plug in the current tau, and that gives me the right-hand side here in this Newton system. Okay? So this is a system that defines the steps. All right? I can break down that last row, that third row there, into individual components, because these are both diagonal. So if I look at it one component at a time, I just get si times delta xi plus xi times delta si. The corresponding component from the right-hand side is just minus xi si plus sigma times mu. All right, I can sum that over both sides, and I'll get, this turns out to be useful later on, believe me. Okay. Well, I shouldn't say believe me, because that's a flag these days for I'm about to tell a lie. That's what, no. But I don't mean I'm about to tell a lie. Okay, so I have to stop using that phrase. All right. Okay, so if I sum both left and right hand side from I equals 1 up to n, I just get S transpose delta X here, I get X transpose delta S here, I get minus X transpose S, which I've already told you is N times mu. And then here, when I sum that out from I equals 1 to N, I just get N times mu times sigma. So if I keep track of what's happening here, the summation here is just minus 1 minus sigma times N times mu. Okay, so it sort of tells you the linear prediction of how much you're going to decrease the average, the duality gap, the scale duality gap, essentially. Now, if you look at this system, this is a linearization of that f of tau system. The f of tau system is almost linear as it stands. The only thing that's stopping it being linear is the x times s terms. So the only thing I've left out here, if I put in the delta x delta s times e term, I'd have actually an exact relationship. I would have solved the nonlinear system. So the only thing that's stopping x plus delta x, z plus delta z, s plus delta s actually solving the original system is this term, okay? So that's the term that I need to keep track of. I want to keep track of how big that is, how far I am from actually, the difference between this system and the real system that I want to solve, the real nonlinear system. So again, I'm using this notation where I'll take delta x and I'll turn it into a matrix by just spreading its elements out along the diagonal. And so these are going to come up in the analysis. So the analysis is mostly concerned with showing that this term doesn't get too big. So you don't pay too big a price by ignoring it in this Newton approximation. Okay, so here's this diagrammatic picture that sort of explains what's going on with these methods. And it's a nonlinear geometry, but I think it's nicely illustrative. So here I'm dealing with a case where there are two variables, little n equals 2, and I'm plotting on the x-axis the product x1, s1, and the y-axis x2, s2. So in that geometry, the central path is just this line at 45 degrees, where the xi, si, x1, s1 equals x2, s2. Okay? The n minus infinity neighborhood is just the one that says they both have to be roughly the same size. So I can't have x2, s2 being way smaller than x1, s1, or vice versa. So the boundaries of this n minus infinity neighborhood are these dotted lines. Okay? So I can sort of illustrate what's happening at every iteration by saying, okay, if you give me the current point, it corresponds to a point in this kind of weird geometry. If you calculate the Newton step, it traverses a quadratic path in this geometry, right? Because the path is parameterized by alpha, and xi times si is a quadratic in alpha, as I just mentioned a moment ago. So these you can think of as being quadratics. I stop as soon as I hit the boundary. Okay, I pick the alpha to stop when you hit the boundary. And then I just repeat that process. Now, how do I know that I'm always heading inside? Well, the Newton step, if I take a linearization of that initial direction that the trajectory is carving out, it's actually heading for the point on the central path defined by sigma times mu. Okay? So to first order, you're heading for this sigma times mu point. But of course, because of the nonlinearity introduced by the delta s times delta x term, it sort of tends to veer off and then bumps into the boundary again. And that process repeats. But it turns out you can move a significant distance before that happens. You don't just immediately go infeasible. You can take a reasonable step. And that's the secret to showing that you get a reasonable decrease every time. Okay, so I'm not going to go through all this in detail because it's 2:10 in the afternoon, but this is the complete proof that if you start from an initial point that's in the n minus infinity neighborhood, important caveat, but if you just give me that, I can give you the complete proof of complexity, okay, ending up by showing that you get this amount of decrease at every step. And these are just 5 statements. The proof of each is exactly one slide, and each one follows from the one before. So it's just a chain of implications. The first one is purely technical. If I take 2 vectors in Rn with a positive inner product, then it's sort of an implication of the geometric arithmetic inequality, as we'll see on the next slide. Okay, so matrix U and matrix V are just what you get by spreading. I needed to have diag here, sorry. I need diag in front of those. But it's what I get by taking U and V and just making diagonal matrices out of them. Okay, from that I can deduce that if you take the 2 particular steps, the primal and dual steps, and take the matrices generated by those and apply this result, I get this inequality that sort of bounds how big the nonlinearity is, essentially. Using that and using the fact that the current xs is in the n minus infinity neighborhood, I can find a bound on the right-hand side here. Okay? So that's how I get to statement 3. From that, and this is kind of the key step, from that I show that I can move at least this far along the search direction. That is all alpha between 0 and this upper bound are guaranteed to be in the n minus infinity neighborhood. So I'm not going to bump into the boundary. What's that?
What is gamma?
Oh, gamma defines the n minus infinity neighborhood.
Okay.
Okay, that's the thing here. It's something between 0 and 1. Okay, and the sigma here, that actually needs to be sigma min. Okay, but the sigma defines the range of values of sigma that define how far along the central path you're trying to move, how much decrease you're trying to get out of this iteration. Okay, so you're able to show that you can take a significant step. And then it follows from that you get at least this amount of decrease on the current iteration. So it's just 1 implies 2 implies 3 implies 4 implies 5. This is actually the most technical one. And Aleksander forbade me from proving this, so I'm not going to go through it all. But I'll just point out that all it is a consequence of the scalar arithmetic geometric mean inequality. You just take the U transpose V, you break it up into terms where the U is positive, the UIVI is positive and the UIVI is negative. You use the fact that the 2 norm is less than the 1 norm. I don't know, that's pretty much it. That's pretty much it. Okay, I'll leave you to contemplate this later on if you want to follow all the details. But that's it. That's the first statement. Okay. So how do we apply that to get the second statement? Well, the second statement, remember, is this bound here. So the trick is to figure out what to call U and what to call V, and it's not what you think. It's not U equals delta X and V equals delta S. You actually need to apply a scaling to them. And the scaling you get by taking the X and the S, the current iterates, the diagonals formed by the current iterates, taking their product, and taking the negative square root of that. And you get another diagonal matrix. Now remember, X and S are both strictly positive, so all this is well defined. X times S is a positive diagonal matrix, so I can take its negative square root. And what I'm going to do is hit both sides. This is the third row of equations in the Newton system. I'm going to hit both sides by D. Well, actually, yeah, by D. I'm going to hit both sides by D. And I get this kind of scale version of that system. So now I'm going to apply that first technical result. Yes?
There are methods that are based on doing that operation and then doing a Newton step, right? Like meaning that you actually rescale. What are those? I forgot. What
Well, there are things, some of the methods for STP basically do that.
I see. That's like Nesterov-Todd.
Yeah, they're sort of Nesterov-Todd scalings, yeah. But we don't necessarily need to. You can do that. I think you can do that for LP, but we don't have to. Okay? So, so when so I get this, I define U to be this guy, V to be that guy, and so this is telling me what U plus V is, and U plus V is the thing that comes into the right-hand side of this first technical result. So applying that first result, I get that the U times V times E, because of course U times V, if I multiply that out, the D inverse and the D cancel, okay? And so I'm just left with delta X times delta S times E. So that's how I get that. Is less than or equal to 2 to the minus 3 over 2 times the norm of this thing, the stuff on the right-hand side squared. Okay? So that's a straight application of the first result. So that's the proof of the second one. Okay, the proof of the third one. Well, all I need to do is to just take the right-hand side from the second inequality. It's the square of a vector. It's the 2 norm squared of a vector. I just expand it out. When I take the inner product of this thing with itself, I just get X transpose S. When I take the cross product, the XS to the 1/2 cancels with the XF to the minus 1/2, and I just get E transpose E, okay, times a scalar. So that's nice. And then when I work on the last term there, that's a little bit more complicated, but again, I use the fact that XS belongs to this n minus infinity neighborhood. So I know that these pairwise products are greater than or equal to gamma times mu. Okay? So when I take the inner product of this with itself, I get 1 over xi si, but I can upper bound all those terms because of this inequality here. I can upper bound them by 1 over gamma times mu. Okay? And now I just take use the fact that E transpose E is just n. I can just mash it all together, and I get this upper bound. Okay? So that's the third one. The important thing to notice about the upper bound is it's got an n in it. that turns out to be significant. That's where the order n log epsilon complexity comes from, and it's also got a mu in it. That's important too.
Steve?
Yes.
So just for, I know this is going to come up later. Is there any reason why we might expect that that n is being pessimistic? Like that there's some loss in this kind of analysis?
Yeah, it's not obvious, but when you go to using the 2 norm neighborhood, that n sort of turns into a square root of n for reasons that maybe have something to do with like the inequality between the 2 norm and the 1 norm. I'm not sure. But I don't think there's an obvious way to keep using this big wide neighborhood and do better than this n. I don't think there's an obvious way. Yeah.
Maybe there's a naive question. I wonder if you can give some intuition to the following, right? You're somehow proving that even if you're at the boundary in terms of one of the xi being equal to you can still get a sizable improvement.
Yeah.
Is there a way to see that intuitively without?
Yeah, if I go back to this picture here, if you don't put that sigma damping term in, you're going to be trying to take a Newton step directly for the solution here, and the danger is that as soon as you start moving along that direction, you're going to go infeasible. Okay, so being aggressive and aiming for this, that is an algorithm, by the way. It's called affine scaling, and I'll talk later about algorithms that use directions like that. But you can't just use it at every iteration because you may never make progress. So as I mentioned earlier, by just targeting a point that's somewhere further along the central path, the Newton step starts out heading for that point. Okay, so the tangent to this direction is actually going to be a point on the central path. So that's telling you that you're going to start out moving internally to this neighborhood. Now, as to the fact that you can actually move a substantial distance before you hit the boundary again, that really comes out of that analysis. I'm not sure how to do that intuitively. But that comes out of those 3 inequalities that I just proved. Was there another question? Yeah. All right.
I think we got a little bit lost in our implementation.
Okay.
So where did we enforce that xi, si is greater than or equal to gamma times?
Oh, we're assuming that that's always true. So
we basically pick our steps. So
that's true at the first step, and we picked a step to make it true at all the subsequent iterates. Okay?
okay.
So we're explicitly enforcing that.
And tau is also something that's fixed throughout the...
The tau is the sigma times mu. So tau is my generic notation for sigma times mu, which changes at every iteration. Yes, it's changing.
Intuition for tau, it's basically our duality gap that we're trying to decrease.
You're trying to shrink it to 0. So you're trying to, at every iteration, you're trying to move a little bit, you're targeting a point a little bit further along the central path towards the origin. Okay.
Thank you.
A question?
Yeah.
I'm trying to figure out if gamma should be large or small. Because the
Yeah.
lecture says if gamma is large, the quadratic lengths are longer. But if gamma is small, I'm closer to the central path.
Yeah. In practice, you sort of pick gamma to be small, close to 0, to give a nice wide, give a lot of latitude. What price are you going to pay for that? Well, not too bad. I mean, if gamma's small, I guess the upper bound in alpha gets kind of small. And so the theoretical complexity might suffer a little bit. But it turns out that in practice you kind of want it to be small.
So if gamma small means the cone is thin or
Big. No, it's big. Yeah. It's almost the whole space then. Okay. But you just got to pay. This is one of many instances that I'll talk about later where the practicality kind of is in conflict a bit with the complexity. Okay. I'll mention that. I'll say a little bit more about that later on. Okay, so we've proved the third statement. We're up to 1, 2, 3. Let's see. We got up to here. This one here, this, as I said, is the critical one. This actually, I lied to you earlier when I said believe me. I was actually lying. But this one actually takes a slide and a half rather than one slide. Okay, because as I pointed out talking to Ben earlier, you want to show that you stay inside this neighborhood by taking a step alpha along the path. So you have to keep track of what's happening to the xi-si's, which is the left-hand side of the inequality defining n minus infinity gamma. You also have to keep track of the right-hand side, which is mu of alpha. They're both quadratics. Okay, the xi-si product, I just expanded out using the definition of what you get by stepping a distance alpha along the Newton direction. The term involving alpha you know exactly what that is because of the third block of the Newton equations. Okay? The third block of the Newton equations was just this. Okay, so this tells you right away what the coefficient of alpha was. Okay, the last term here, we just worked hard to bound that term. The product, the nonlinearity, the product of the two steps, primal and dual. We've got an upper bound on that, and that's what I use there. That comes right out of Formula 3. So I'm able to lower bound the right-hand side, the xi/si, by this quantity, which is quadratic in alpha. Okay? I can say exactly what the right-hand side is, the n times mu of alpha, again by just expanding out what do I mean by x of alpha, s of alpha. Again, I write it out as a quadratic in alpha. I again use the third row, all that hard work I did back here when I summed up the components of the left and right-hand side. That gives me the coefficient of alpha in the expression for mu of alpha. So I can replace that by this. Okay. And so that gives me this coefficient here. That's what I've done to get to the last line. And again, I can use that upper bound on delta x, delta s to bound that last term. No, in fact, I don't have to do that. I tell a lie. That actually is 0. That turns out to be 0. And did I prove that somewhere? I can. So two of the Newton equations are that A times delta x equals 0, and A transpose delta z plus delta s equals 0. Okay? So if I just take that last one and multiply it by delta x transpose, okay, I just get, the first term goes away because I get A times delta x equals 0. So I'm just left with delta x times delta s equals 0. Okay, so, and that's what I use to get rid of that last term. Okay, so that goes away. So I actually just get something here that's linear in alpha. And I can say exactly how it depends on the current value of mu defined by the current iterate. So I can show what happens to mu as I take a step along alpha as a function of the current value of mu. Okay, so now if I ask the question, how big can I make alpha and still stay in this minus infinity neighborhood? As long as I can show that the alpha is big enough so that this is bigger than that, then that alpha is okay. All right? This is a lower bound on the left-hand side. This is equal to the right-hand side. So that's all I need to do. That's the lower bound on the left-hand side. This is the right-hand side. I can just figure out what's the biggest alpha that makes this true. That's it there. Okay, so that gives me an upper bound on the alpha that I can take. Of course, you could possibly... I use bounds to get that, so the alpha in practice could be longer than that. But that's you can go at least that far.
So again, here,
Yeah.
so when gamma is small, that expression is just the leading term of gamma is what's going to be dominant. So it goes small.
It's small, yeah. Gamma small will make this upper bound small, yeah. Yeah, which is a little bit counterintuitive. This is kind of intuitive. The sigma, so the sigma is what factor of decrease you're trying to get out of this step. Okay, so if you're trying to be really aggressive and you're trying to go from mu to mu over 10 or mu over 100, you know, so in other words, sigma is 0.1 or 0.01, then you won't be able to move very far because you're being really aggressive and you're sort of targeting a point close to the solution. So the fact that it should be upper bounded by sigma makes sense, but the gamma is maybe a little bit less intuitive. It just, I guess it sort of says that you're playing with fire if you're going to allow a very wide neighborhood, I guess.
Because you're always operating close to the boundary.
Yeah, you're always operating very close to the boundary. So you're only going to be able to take small steps, small but not trivial.
I guess that was Robbie's question, I guess.
Yeah, okay. Okay. Okay, and here's the last one. This fits on one slide. So this is what happens to mu as you step along the distance gamma. So we just have to keep track of mu as a function of alpha. I know that because this is linear in alpha, and because sigma is less than 1, this is actually decreasing for alpha between 0 and 1. So our best strategy is to move as far as we can until we hit the boundary. We've just proved that we can move at least this far before hitting the boundary. So that gives me a bound. It gives me an upper bound on how bad mu k of alpha is. Here it is here. And that's exactly what I'm looking for. So this has the form 1 minus delta divided by n, where the delta involves here the sigma min, I guess. I'd be conservative. It involves gamma. It involves 2. That's it, right? And the n only comes in here. Okay, so that's, oh yeah, here's the delta here. So that's what we needed to get a polynomial type complexity result. And nothing I used, yeah.
Sorry, I just want to make sure I remember so sigma is the...
Between 0 and 1. So I'm bounding sigma strictly away from 0 and 1.
You pick it, or you could pick it.
You can pick it adaptively. In fact, practical methods use adaptive heuristics to pick sigma.
If we had it be a constant, it's saying that probably the best value would be...
Well, this is suggesting 1/2, but you know, how much credence do you place in worst case analysis? You know, but in practice, you know, Mądry came up with this very slick heuristic in like 1989, which was basically an adaptive way of choosing sigma, essentially, with a few other bells and whistles. But you know, the thing is, when you get close to the solution, you can get more aggressive. You can pick sigma to be closer to 0. When you're further away, sigma equals 0.7 or 0.8, you know, is pretty much guaranteed to give you a nice, a decent step. Okay, so that's it. That's a complete end-to-end, except for choosing the initial point, analysis of polynomial complexity of this long step path following method. Okay, well, let me talk about how I've got 5 minutes. Good, yeah. Okay, so I can tell you about some other variants that use basically the same idea, namely solving this system, this algebraic system, targeting a central path point. Here's a method that uses a much narrower neighborhood, the n2 neighborhood, which, as I pointed out earlier, is not nearly as generous as the n-infinity neighborhood. So if you start out in the n2 neighborhood, you compute Newton steps. It turns out that here, as long as you define the n2 neighborhood by theta equals 0.4, you can actually take a full step and stay inside the neighborhood. You don't have to do a line search. That's why it's called a short step path following method. So no need to choose an alpha. You're just guaranteed to stay inside the method, the neighborhood. You also have to choose sigma like this, just a little bit less than 1. 1 minus 0.4 divided by square root of n. Okay? So it's a very conservative strategy. It's just kind of creeping towards a solution and guaranteeing this amount of decrease at every step. But this ends up with better worst case complexity. You get a square root of n instead of an n. Okay? And these are the best known results for these kinds of methods, a square root of n. However, this is slower in practice. You can implement this perfectly easily. It's very easy. Yeah, it's trivial to implement. You just need a linear equation solver to compute that step, but it turns out to be slower.
Which one's easier to initialize in practice?
Yeah, we'll talk about that. Yeah, we'll talk about that. Okay. Here's another variant, and this is probably the last one I'll talk about before the break. This is so-called Predictor Corrector. So this one I can sort of draw a picture to illustrate what's going on here. This one actually worked with two neighborhoods, a wider one and a narrower one. And it does a predictor corrector thing. It starts out in the narrow neighborhood and then takes a Newton step, but stops at the boundary of the wider neighborhood. So it has to do a line search to make sure that it doesn't violate the wider neighborhood. And then it does a corrector. So it computes a step from that point with the goal of getting back into the narrow neighborhood. And in the corrector step, you don't try to move any distance along the central path. You just try to recover centrality without making any progress. So what does that mean? Let's go back. What it means is that in the second Newton step, you're just solving f of mu k. There's no sigma here. You're just kind of trying to recover centrality while not trying to decrease the mu. In the predictor step, you do try to decrease the mu. In fact, you try to decrease the mu all the way to 0. Okay? So you take an aggressive step targeting the actual solution of the primal dual LP pair. So why don't you get stuck at the boundary? Because you're starting from the inside neighborhood, and you don't have to stop till you get to the outside neighborhood. So you can make a significant step along that aggressive direction because of the gap between the two neighborhoods. Okay, so you alternate between these taking these aggressive steps and taking these corrector steps, which are just trying to recover centrality. So you can think of the sorts of method I've described earlier as kind of hybridizing between these two. Instead of switching between 0 and mu, you take some intermediate value sigma times mu. So you're sort of rolling the two steps into one. Okay, I think it's a good time for a break.
What's the complexity of this?
This is also square root of n. And the analysis is very similar to the, it's very similar to short step path following. So this is also better than long step.
Does this perform in practice still worse?
Yep. You can actually show that it converges superlinearly, but it's still slower on the early iterations. Okay. Time for coffee. Thanks.
Once upon a time, the Holy Grail was sort of showing that there was lots of logarithmic number of iterations.